Test 1, 2, 3. Test 1, 2, 3. Who's not here? I don't see AJ and I don't see Darby. Is that true? Who else are we missing today? Is it Evan? Okay. Well, it's okay. What's that? What's that? With you have inside knowledge?
The opposite.
All right. All right. Well, I'm gonna record today in case so you have to be on your best behavior. No, you don't really. I need to be on my best behavior. You guys are probably not going to get picked up well on this microphone, so you can be disruptive and all those things, and everything will just be fine. All right, so I do wanna pick up before we get into our case. Strange, why is that showing up there? That seems very odd. Okay, I don't understand that, but that's okay. So I do want to pick up where we left off before we get into the case study. So I want to spend about half the class on this case study. And I see that some of you have nice notes scrawled out on your case study. That's good. The more you think about these things ahead of time, the better. And we were going to do this last week, so maybe not fresh in your head, but hopefully my reminder got you going there. So we were talking about energy in systems, and we had moved from a discussion of energy in systems in general, where we talked about how the Earth is this structure that disproportionately receives energy near the equator, and that all of the movement of air masses and water masses are really kind of, I won't say designed, because that implies that there's the problem with our language as human beings. And I've been thinking about this, actually kind of goes back to our conversation about like the intentions of ecosystems. I've been thinking quite a bit about like that discussion we had in which I think at least one of you was slightly upset my contentions about ecosystems, about there being no such thing as ecosystems health. And when we talk about why systems are the way they are, we have a tendency to say that they want to do something. Of course, they don't want to do anything. They do what they do, following whatever sort of physical and biological principles have developed over time. But nevertheless, I think as human beings, because we function with this idea of intention, it's just easier to talk about systems as having intent and having goals. But ecosystems have neither intentions nor goals. They just function according to whatever rules have developed over time. And, in ecological systems, those are kind of evolution, selection pressures, what occurred here. So I have a tendency to say things like, heat wants to flow from hot to cold, because that's what thermodynamics, but heat just does that. It doesn't want to do that. There's no intention on its part. That's just what it does by thermodynamics. So when we look at systems and how they deal with energy, they want to dissipate energy. I say they do dissipate energy. That's kind of what they do. And that's a rule that occurs at all scales. And the way it works is different at different scales. But like we were talking about, because more energy enters the Earth at the equator, you get this poleward movement of heat, and that poleward movement of heat, as that heat is dissipated out into space, is moving air masses and water masses, warm air masses and water masses, northward and southward from the equator, and that's what results in our and the dissipation patterns. Wind currents, water currents, they're just dissipative patterns that developed as a result of the physical system having constraints like land masses that don't allow water to move across land. And so water has kind of convoluted gyres, is what we call it when water is moving, as opposed to wind patterns. But that's just what's happening. But we talked about the idea that in living systems, one of the great innovations of evolution, if we can call it that, again, innovation implies intent and there's no intent, but one of the great innovations of evolution is life being able to break energy down into these discrete little transformations And for life, it's about chemical reactions. And essentially all of the chemical reactions that are involved in energy are oxidation reduction reactions. And that's why we care about oxidation reduction reactions, because anytime you talk about energy in a living system, you're talking about electrons being moved from an electron donor to an electron acceptor, and life using that process of the shifting electron to do the work that it needs to do. And so that's how the system works, and that's why we end up talking a good deal about, oxidation reduction reactions. And, some of them are oxidation reduction reactions in which we're actually taking low energy compounds and we're creating high energy compounds. And the reason that doesn't violate the second law of thermodynamics is because there's an energy source coming in to drive that unthermodynamically favored reaction is driven by a thermodynamically favored reaction. So, that beautiful fixation of sugars in the leaf of plants that occurs in the Calvin-Benson cycle, photosystem 1 and 2, etc. It is all about shifting electrons. Everything going on in here is shifting electrons. By the way, this ribulose bisphosphate ribisco carboxylase, this is the most prevalent enzyme on the earth. There's a lot of photosynthesis going on, so that's a big one, that particular one. But at any rate, we're driving these reactions, and in general, photosynthesis is about taking sunlight and turning it into chemical energy by reducing carbon into organic matter. And then photosynthesis is about taking that organic matter and oxidizing it to turn it into CO2. And that's the center of it all in living systems, are these major key oxidation reduction reactions, which are central to driving just about everything in our living system. So those are at the center of everything. Photosynthesis and respiration and the general, and of course we fix it into different kinds of organic compounds, and we can convert these carbohydrates, which CH2O6 is sort of a generic carbohydrate. It's sucrose, it's glucose, it's cellulose. All of those things are essentially CH2O6 on cellulose. We just take sugars and we make these really strong bonds. I say we, the plants do this. They make these really strong bonds. So it's sugar, but it's sugar that really doesn't want to break apart and is really recalcitrant carbon. It does not want to be eaten. You have to have special microbes in your gut to eat it because it's a really strong bond, but it's essentially just made from sugar. It's just a linked set of sugars. Starches are linked sugars. And then of course you can convert them to lipids, which are a little bit different, but it's just organic matter. So anyway, we've been through all that. We talked about the dam. That is Niagara Falls, isn't it? Have any of you been on Lady of the Mist? No? You guys, it's worth it. You're not far from Niagara Falls. It's worth it. Just as sort of like a kitschy tourist experience. If you get a chance, go there. It's like a cool experience. It's a lot of history in that. Anyways, we've talked about all that. We got here. Very, very important. This is very important because it just explains so much of what's going on in systems. And we were talking at the end of yesterday's lab when we were over there about the chemoautotrophic bacteria of the world, and most people thinking that they live in deep hydrothermal vents, that it's these weird clams and worms and stuff like that are eating stuff that I don't even have up here, but it's reduced sulfur that they use as an energy source for everything. But what the local chemoautotrophic bacteria are doing is lots of them are using NH4. Some of them are using Fe2+ as energy sources that they are shifting to oxygen. So when we look in the soil, changing color of soil, there are microbes in there that are using, when there's oxygen present, there are microbes that are using the reduced iron, the ferrous iron, and they're oxidizing it into ferric iron, but there are lots of microbes everywhere taking ammonium and turning it into nitrate, which is, as I say, why if you're in like a natural body of water around here, you're not going to find a lot of ammonium, because the nitrifying bacteria, which is the name of the buggers who eat up NH4, will have turned it into nitrate because it's a good food source for them. And that's mostly what goes on in the front end of a living machine. You break apart organic matter, and then there's tons of ammonium present. And as soon as they hit oxygen, they start consuming that. Actually, I had a great, well, I won't go into it. We had a really neat project where, well, some cool biogeochemistry going on there. So, you can talk about reduced forms of an element and the oxidized form of the element. And you can talk about the redox potential of shifting the electrons from the reduced form to the oxidized form. And you guys were measuring the ORP, the oxidation reduction potential. You were measuring the oxidation reduction potential of the soil. And again, it is kind of a squirrely probe, so I'm not going to say you were accurately measuring it, but you were measuring it. That was the point of doing it, so that you can kind of tell what kind of an environment is going on there. What you're essentially doing is you're looking at the dam. You're asking the question, where are we? Where is the outlet of the dam when you measure the oxidation reduction potential? Because it's going to tell you what kind of reactions might be able to occur in that soil, given how reduced it is. Now, I'll say a couple things like, I just want you to practice using the technique, but for ORP in particular, it doesn't make any sense to do it on soil that you've taken out of the field and dried. You really want to do it in the field because the oxidation reduction potential is going to change as soon as I dry the thing. So again, giving you experience with the probe, but I would trust none of the oxidation reduction potential numbers because the soil is out of its environment. As opposed to pH, which is a little bit more conservative, it's likely to be okay. The conductivity, regardless of whether that probe was being a little bit of squirrely too, conductivity should not change as a result of taking it out of the field very much. So at any rate, but ORP is really a field measurement. Okay, so we've talked about that. I want to move on. We've got the top and the bottom. This is just an example. Don't go writing this stuff down. I just want to say whenever there's oxidation going on, there's reduction going on. They're always paired reaction. And I just wanted to give you an example, but don't write any of this down because it's not like I expect you to know this. I'm just saying, like when we talk about oxidation reduction, there are two half reactions going on here. There's the thing that's being oxidized and the thing that's being reduced. And so here I'm giving you, sort of the example of the oxidation of, one piece of an organic compound and like what its potential is, and then the reduction half reaction. And those two reactions are basically setting where the top of the dam is and where the bottom of the dam is, how much of a gradient there is to get energy out of that reaction. So each side of that half cell, that half reaction, is giving you a sense of like, what's the total amount of energy I could get from this particular transformation. In this case, the transformation of respiration, like how much energy could I get out of that? Where's the top of the dam? Where's the bottom of the dam? Does that make sense? Again, I don't care that you remember like numbers or anything like that here. I'm just trying to give you a sense that most of the reactions that are involved in life, all of them that involve energy, are oxidation reduction reactions. And there's an oxidation side, a reduction side. There's decisions being made about where you're getting your electrons from. That's the thing that is going to be oxidized, and where you're shifting your electrons to. That's the thing that's going to be reduced. And in general, organisms are going to choose good electron donors and good electron receptors. So what's going on in a given environment is going to be set by the redox potential, what can go on. And so then you've got like the combined reaction, the total amount of potential, and we do measure it in volts, so it's just like electricity, the total amount of potential we can get out of the thing. And then, you can do a lot more math if you take chemistry. And I really don't care that you remember any of this stuff. The point is that you can get, this Gibbs free energy function, blah, 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 but you get energy. You can calculate how much energy you're going to get out of this, how much energy you're actually going to get out of a particular reaction. And again, I don't care that you remember it. I just want to give you the sense that that stuff you learned in chemistry about oxidation reduction potential, it does actually control what's going on in an ecosystem. The organisms in an ecosystem are generally going to do what's most energetically favorable. And if you understand that, it makes it easier to understand what's going on in a given aquatic environment or terrestrial environment for that matter. But oh, do I want to talk about nitrate too? I don't think I want. I'll skip over this. This is just another example of a reaction, but this particular one. Well, so check this out. This one, I've got like a big gradient because I'm moving electrons from a really good electron donor organic matter to a really good, my best electron acceptor, which is oxygen. So notice how far apart my two arrows are. I've got a big gradient here. And what I've done for my nitrogen is to show my top rate gradient is just as good because I'm oxidizing organic matter. But in this case, if I don't have oxygen present, I'm going to shift to next best electron acceptors. And it turns out nitrate is an okay electron acceptor, not as good as oxygen, but it will take electrons. It's not as good a potential. It's like having a higher outlet on this. So my voltage difference is not as good. So I'm not going to get as much energy out of doing this. So I get less energy out of I get less energy out of that. Go away. HCO won't go away. I won't get as much energy out of it. But still, if there's no oxygen, that's what I'll do. And this is exactly what we want to happen in the tail end of the living machine. We want this to happen because what we want to do is get rid of nitrogen, which at one level is a really stupid thing to do because we expended all this fossil fuel in the Haber-Bosch process fixing nitrogen. But in good wastewater treatment plants, at the tail end of them, we're trying to encourage microbes to use nitrate as an electron acceptor to accept electrons from organic matter. And we will feed those microbes good quality organic matter so that they shift electrons onto nitrate, because if they shift electrons onto nitrate, they turn the nitrogen into what form? Yeah, I don't totally expect you to know this, but yes. No, no, they don't. I mean, it does go nitrate, but ultimately, what do they turn it into? No, I'll give you a hint. We're breathing it right now. No. Nitrogen gas, 79% of what we're breathing right now is nitrogen gas. They turn it into nitrogen gas. And why would you spend all this time and energy trying to encourage microbes to take this precious nitrogen fertilizer that you've expended fossil fuels fixing to turn into a fertilizer into nitrogen gas that blows back up into the atmosphere? Why would you do that? Yes. Yeah, because if you throw the nitrogen into the water, it's going to cause toxic algal blooms. And in fact, those the toxic algae blooms that have been occurring with increased frequency in Lake Erie that in fact shut down the Toledo water supply for 2 days a couple of years ago. They had to completely shut down their water supply because they had this toxin called microcystin neurotoxin, which produces a byproduct of these algae, microcystis, is encouraged in part by excess nitrogen. Phosphorus and nitrogen are both limiting factors in aquatic environments. Fun fact here, useful fact to know, in general, in marine environments, that is salty environments, nitrogen tends to be the limiting factor. In freshwater environments, phosphorus tends to be the limiting reactant for phytoplankton blooms. But it turns out that those toxic algae in Lake Erie are encouraged by nitrogen as well as phosphorus. But at any rate, that's why we want to get the nitrogen into nitrogen gas. And that's why we try to create in the tail end of the living machine that gravel marsh that the water flows through. Our objective in that gravel marsh is to create an anaerobic environment. Why do we want to create an anaerobic environment in that? Why is it important to us to create an environment that doesn't have oxygen in it? Why would we do that? Yes.
Nitrate's the next best. Exactly.
Yes, if there was oxygen present, there would be no denitrification, which is the conversion of nitrate to nitrogen gas. It's only occurring because we've created an environment in which we have deprived those microbes of this outlet. This outlet, the oxygen outlet, doesn't exist. So they're going to shift up and find the next best electron acceptors. And there's lots of nitrate in the water. So they'll use that. If there's nothing else there, they'll use it. And it's a special group of microbes. They're called denitrifying bacteria that do this. And they won't do it if there's oxygen present, because it wouldn't make sense for them. It wouldn't be energetically favorable. They wouldn't be as good at getting a good deal. I could get this much energy out of the system if I had oxygen. I can only get this much energy out of the system if I'm using nitrate. I'm not going to do this if there's oxygen present. It's just not going to make energetic sense. Yes. We'll do a real quick tour when we do the LM. It'll be really quick. And what I'm giving you now is actually going to be really useful for the case we do on that. But okay, I want to say a few things about sort of the history of studying energy flows in ecosystems. And again, as I'll point out many times, mostly a bunch of white guys, because that's who was in ecology at the time. But the real granddaddies of studying energy in ecosystems are E.P. Odom, Eugene Odom, H.G. Odom, Howard, and Raymond Lindemann, who first came. Lindemann is actually working at Yale University. That's where he did his PhD. But he studied, well, actually, this is Charles Elton. So Charles Elton goes way back in studying energy. He was the first person to begin to do what we now call food webs, but to try to trace out this idea of where does food flow, which is really where does energy flow in ecosystems. So he sort of has this, I have this beautiful antique monograph of Charles Elton's in my office someplace, where he has all these diagrams like this of like how food is flowing in different systems. Lindemann did this bog out in Minnesota. I actually have a picture of one of my former students in this class who did an honors project with me, who is now tenure track ecologist at St. Olaf's College out there. So he ended up getting back there. But he and I are both sitting at the famous bog where Lindemann did his work. We got a nice photo of the two of us sitting there. Anyway, so this has been a very powerful way of understanding ecosystems, is thinking about when sunlight lands, how do we track the energy pathways that it goes through? And there are a lot of different ways to try to track that stuff, track that energy moving through systems. And as we move towards the case study that we're doing today, I want to talk about like some of the ways that we track where energy is going, because it's not like we have some like e-meter. Are you guys familiar with the e-meter? It's the Scientologists have this little contraption they use to measure people's, I don't know actually what they're measuring, but something. But how do you measure energy? You know, really when it comes down to it, you end up measuring chemicals that are sort of proxies for energy. And that's true of like most things we measure in ecology. It's very rare that we measure the very thing itself that we care about. We measure something that is related to the thing that we care about. And so there are, a variety of different proxies we use to measure energy flow through ecosystems. So sometimes what we measure is stocks of energy. So we can go into the forest and we can look at the trees and say to ourselves, I see a lot of energy stored in this system, because all of that cellulose in those huge tree trunks, it's all stored energy. You know that because the thing could catch on fire and it'd be really hot if it caught on fire, and it would burn for a while because there's a lot of biomass there. So you can just see physically all this energy that's stored there. And we can use that tree to measure the accumulation and storage of energy. It's not something you can obviously do on a daily basis, so you can't get a short-term measurement of energy from the tree trunk. But we talked about the tree cores. Like each year, we're putting on this layer of cellulose on the outside of the tree, and that's a measure. So if we calculate how much ring we're adding each year, just as the Hoffman et al. Group did, calculate how much biomass is being added, some simple geometry to calculate the area of that ring, and some guesswork about how tall the tree was at the time, but it's guesswork based on good and what are called allometric equations. We can calculate how much annual primary productivity, annual photosynthesis was turned into that wood over time. So we can measure the changes in the stocks and use that to get a rate. So just to be clear, a stock is an amount of stuff. A rate is the flow of stuff into or out of that stock. And one way to measure that rate is to measure the change in the stock over time. So we can measure the net primary productivity of the forest by measuring the tree rings. That is a measure of net primary productivity in the forest. And those guys did a great job of measuring that.
Two things.
Yeah, exactly. You measure the flux as delta stock. You measure the stock, and the nice thing about the tree ring is you're measuring a stock that went down each year. And because you're measuring a stock that went down each year, you can compare those stocks, and you can measure this tree ring. Everything in this year's tree ring was primary production this last year. So I just divide that stock by 1 year, and that's annual production. So a stock is a rate. It's carbon per meter squared per year in that case. That's my unit for flux or flow is a carbon per meter squared per year. That would be a good thing for measuring terrestrial primary productivity. You want it on an aerial basis because we need to know how much is being fixed in the forest. So you could say, I mean, you could use a bunch of units. You could use carbon per meter squared per year, carbon per hectare per year, whatever you want to use. It's an aerial measurement because it's stuff per area per year that I'm putting down. The stock is how much stuff is there right now. So yes, I mean, I think the answer to your question is yes.
Yeah.
It's simply right. So yeah. So just to repeat what I said earlier, one way to measure the rate of primary productivity is to measure the change in the stock, right? As the stock changes, because I said inflow equals outflow plus storage. You're measuring the storage when you measure rate. But no, you're not measuring inflow and outflow. You're measuring net primary productivity. You're not measuring primary productivity because primary productivity is all the carbon that was fixed. And most of the carbon that those trees fix is respired and instantly goes up into the atmosphere. So most of it is not stored. It's just it's a bit of the excess that's stored. So even when you guys are growing, even when you're in your sort of growth phase, you have a lot more energy going into you and going out of you than the energy that's accumulating in you. It's just a little fraction of that energy. So you are a through flow system. You eat, you go to the bathroom, you respire. So you've got an inflow of materials, you've got an outflow of materials. But when you're in, you guys are probably pretty much full grown right now. But when you're in a growth phase, you have more inflow than outflow. And so you can measure that rate of growth. But the important thing to consider is that's not the total through flow of energy. That's just the energy. That's net primary productivity, not gross primary productivity. For a plant, gross primary productivity is all the energy that went into you. And gross primary productivity is always going to be much, much larger than net primary productivity because gross primary productivity is all the energy that the plant needs to do all of the ongoing work it's doing of getting the water up into its leaves, building biomass, doing a lot of respiration all the time. So they are net primary producers. They're primary producers because they have a net accumulation of carbon, but most of the energy that flows into them because of thermodynamics is being used up and flowing out of them pretty quickly. Every night, those plants are respiring and losing most of what they fixed during the day. Even during the day, most of the energy coming into them is being instantly used up in respiration just to keep their systems running because of the second law of thermodynamics. So most of it's going off, but there's that net accumulation. Okay, so biomass is one thing. We can measure flows as change in biomass over time. That's what we just talked about. We can measure shorter term flows by measuring fluxes of gases. So we can measure CO2 changes over time. And we do this. I don't do this. I say we as ecologists do this. We can put a leaf in a little chamber and we can actually measure the flux of, you can put it in, there are little contraptions now. I mean, scientists are very clever about these things. You can attach little things to leaves and you can measure its instantaneous capture of CO2 and release of oxygen. You can do that, you can just do it. And similarly, in some cases, we're using CO2 as a measure. I think I may have already measured, corn is so productive when it's really cranking that you can measure if it's a still day, you can take a little CO2 sensor and move it up and down. You can hold a CO2 sensor and move it up and down through the corn above the layer of the corn, and you can measure a gradient of CO2 because they are depleting. They're sucking in so much CO2 while they're photosynthesizing on a sunny day. It's pretty still. I say still because if there's a lot of wind, there's just enough turbulence to mix the air and you're not going to measure the gradient. But you can measure that. Now, the thing is, that's not a quantitative measure because it's diffusing, calculating rates of diffusion. It's too complicated. I mean, you can see if the CO2 is lower within the corn than it is above the corn, then you know that there's net photosynthesis occurring because otherwise you wouldn't get that gradient. But turning that into a quantitative number of like how much carbon they're fixing, that doesn't really work. So, it's a little challenging to do that. But you can also measure other things too. So we use CO2, we use O2, and I'm going to talk about these in water because it turns out these are great measures of photosynthesis in water because you really can measure oxygen and CO2 in water pretty easily. And as I've mentioned before, and I'll say again, CO2 and oxygen diffuse very slowly across the air-water interface. They do diffuse across the air-water interface, but especially on a still day, there's a lot of turbulence and waves, they diffuse a lot more quickly. But if it's a still day, you can just stick an oxygen probe into the water, as we did when we were out in those wetland ecosystems. And if oxygen is higher than saturation, which we measured in both of the ecosystems, I believe, then we know that the thing has to be photosynthesizing because it's super saturated for oxygen. It's got more oxygen than the water would hold at equilibrium. And the only way it can have more oxygen than the water would hold at equilibrium is if there's an excess of photosynthesis over respiration going on. Does that make sense, everyone? Right, but we can also use other things, and we do use these other things. We can measure decreases in nitrogen in systems, and that nitrogen is the only way that nitrogen is going to disappear in the system is, assuming it's not undergoing some sort of precipitation or something like that, which nitrate and ammonium don't really do that. If the ammonium and nitrate are disappearing, forget about ammonium for a second. If nitrate is disappearing from the water column, and it's an oxidized water column, the only place for it to be going is into plants. So you could use the decrease in nitrogen as well as a measure of net primary productivity. So all of the reactants that are used in photosynthesis can be used to measure the rate of decrease of those reactants can be used to measure productivity, or for that matter, the rate of increase of those things can be used to measure respiration. I mean, in this case, it would be the rate of CO2 decrease, which we would measure as primary productivity. It would be the rate of O2 increase, because CO2 is being used up in primary productivity, O2 is being released in primary productivity. So we use those as measures. And then, again, I'm going to repeat stuff that's in the case here right now, but it is important that you get in your head the sort of jargon that's used for measuring energy storage and release in ecosystem. Primary productivity as a general term, primary production. When we say primary production, what we usually mean is organic matter that's fixed through photosynthesis. So that's a term that's often used as generally referring to as stock, primary production, the accumulation of organic matter fixed in ecosystem. Primary productivity is the rate of that production over time. So these are pretty general terms. And people sometimes use these terms a little bit differently. So you got to kind of watch how people are using these terms. Usually they'll operationally, if you're reading a paper, they'll operationally define what they mean when they use terms. Secondary productivity is the organic matter assimilated by primary consumers. So that's how much carbon they're getting by eating, photosynthetic material. Gross primary productivity is the total amount of organic matter fixed by autotrophs over time. And then respiration is the oxidation of organic or of oxidized matter over time. And then we get to net primary productivity, which is gross primary productivity minus respiration. Organic matter for secondary productivity. Well, as a secondary producer, you're eating organic matter. That is, if you're secondary production, you're an animal or some entity that eats organic matter, and you're taking it in, and we call that process of taking it in assimilation. So as opposed to photosynthesis, it's assimilation once you're a consumer. You're assimilating that organic matter into your body. You're just taking it into you. Yes, digestion is part of assimilation, is just the act of putting that organic matter in you. It'll then go through digestion, and much of that organic matter will pass out your tail end without actually having been assimilated. So not all of it is assimilated through digestion, but yeah. But these, by the way, all of these definitions are carefully outlined in your handout here. So if you have your handout for today, it's all there. All these definitions are there right here on page 5. NPP, R, GPP, NEP. Yeah, actually, I think they're defined in a couple of places in here. So there you go. Now, again, things are the term, depending on time scale, these terms can be used a little bit differently. So I'm giving you some general definitions here, but watch out because people use them slightly differently. So net ecosystem production. So net primary productivity is how much organic matter the primary producers are fixing into their tissue. So they've got energy flowing into them, they're trapping in organic matter, but they always have energy flowing out of them. And so they're always respiring. Every photosynthetic organism is respiring all the time while it's photosynthesizing. So net primary productivity is how much they've taken in minus what's gone out. So that's what's stored within their tissues. But if you think about that at an ecosystem level, and you're asking how much is the ecosystem storing, that's how much are the primary producers storing minus how much are all the consumers, the heterotrophs, eating. So that's how much would be stored in the ecosystem. So if we think of our forest, the plants are photosynthesizing, they're respiring, and then there's all the bugs the bugs and chipmunks and everything else that's eating this stuff. So they're part of the respiration too. So when you look at that wood accumulating in the forest, that's actually stuff that's accumulated above and beyond what's been eaten by all the organisms that are consuming net primary productivity.
You can get that.
Yeah, you could. The question for all of these things is how the heck do you measure it, right? So it's like, yes, in theory you could, but are you measuring all the little squirrels going in and out of the forest and calculating how much weight they have as they enter the forest and how much weight they have as they leave? Because that's kind of what you'd need to do, and putting them in little reaction chambers and measuring how fast they respire stuff. So it'd be a challenge to do, but in theory, sure. You know, all of these things you end up needing to operationalize to figure out how the heck are we actually going to measure this thing that we want to measure versus like the theory of the thing we want to measure. And we almost never in ecology directly measure the thing we want to measure. And you're freezing up on me, aren't you? All right. So here's where we get to sort of like, okay, let's operationalize this and figure out, we're ecologists. We actually want to measure stuff. We want to know what's going on. And we know we can't measure every chipmunk coming in and out of the damn forest. So we're not going to do that because it's too complicated. So there are a bunch of techniques we use, and you know, you usually learn these techniques if it seems sensible to use them. I've actually never used carbon-14 technique. A lot of my colleagues did, but it wasn't necessary for me to do what I want. But we can track, you know, most carbon is carbon-12, but there's carbon-14 out there, and it decomposes to form carbon-12, and you can measure, you know, you can measure its rate of nucleic decomposition. So if you tag stuff with carbon-14 and let ecosystems take it up, you can then trace where that carbon-14 goes and how much of it is sticking around. So people use carbon-14 to measure, you know, because again, organic matter is our key, you know, energy form in ecosystems. If you track where carbon is going with carbon-14, you can kind of tell what's going on. For many years, because the pH probes were invented a long time ago, pH is really easy to measure. People used pH actually to measure in aquatic ecosystems, to measure primary productivity. Now, so let me ask you this. You have to think a little bit here. How would you use pH to measure primary productivity in an aquatic ecosystem? What's going to happen to pH over the course of the day? This takes a little bit of thinking. And what you need to, I think someone did spot on Blackwood. This is actually what, yes. So it was found the other day, but here's the important thing to know for this. Okay, I was trying to say this yesterday, but I'll just write it up here now. So this is like the thing for you to think about when you think about how pH would measure, would be an indirect measure, how it could be an indirect measure of primary productivity. Does that make sense what I just threw there? Yes, Darby. How are you feeling, by the way?
Thank you. I'd say that the pH probably is based on what you just wrote there.
So you're saying, so pH would increase if CO2 were increasing or decreasing? I guess that's the thing that.
If CO2 decreases.
If CO2 it goes, if I have more CO2, I'm getting more H plus.
Yeah.
Right, so you're saying over the course of the day, you'd expect me to have more CO2 in the water.
Oh, I was thinking it more of like the CO2 is, or I misspoke. The CO2 is going into the water, and it's with the water, it's being converted into H2CO3 plus. And so the CO2 is decreasing in the water throughout the day, because it's being converted.
CO2 is.
Yeah, sorry, I meant CO2. CO2 is.
Well, what is happening to this? What else is happening to this CO2? Let me go this way. I've got CO2 plus H2O, and I'm going into H2. I'm going into CH2O, which is my organic matter there. So I've got this is happening too. Yes.
So because CO2, if we remove that from plants photosynthesis.
Right, but this is being sucked at this.
Yeah.
This
At
is.
nighttime,
We're not talking night, we're talking day. So from morning to night, I've got sunlight driving this reaction here during the day. And so what is happening to my CO2 concentration in the water over the day? It's decreasing. So this is going down. And how's that driving? I should have made these equilibrium reactions like this. How's
Also, there's less reactive water, but there's less release, the end of the thing of hydrogen atoms
So I'm driving in this direction.
properly.
And so what's happening to my concentration of H plus if I'm driving in that direction? It's decreasing.
I mean, the page is more.
Does this make sense to people? You look, Kat, you look totally fried there. Okay. Let's start here. I've got CO2. It's going to dissolve in water, right? That CO2 has two possible fates. It can combine with water to form H2CO3. And when it forms H2CO3 is an acid. This is an acid, which is releasing H plus. So that's one thing that can happen in water. If I put CO2 into water, if I were to take a tank full of CO2 and bubble that water with CO2, it would do this. This is, by the way, ocean acidification. We have excess CO2 in the atmosphere. The ocean is absorbing that excess CO2, and the ocean is acidifying. This is ocean acidification happening here because we have lots of CO2 in the atmosphere, and the ocean is acidifying as a result of that excess CO2 from the burning of fossil fuels going into the atmosphere. So in the ocean, CO2 is diffusing. The ocean is what is saving us from being completely cooked. We would have been cooked long ago. The planet would have been totally toasted by all this CO2 emissions, except that the ocean is just slurping down all the CO2, absorbing all the CO2. Problem is it's acidifying the ocean because it's creating carbonic acid. This is carbonic acid, right?
Yeah.
Yes, thank you. It's creating carbonic acid, which is associated with this dissolving corals and just generally screwing the ocean in a gnarly way. So we know that this reaction takes place. Now, CO2 in the water can also be taken up by plants, which are combining it with water. A little bit confusing because it's two reactions occurring with water, but in this case, it's fixing it, right? So this is the process which is slurping CO2 this way, and it's driving this reaction. If you take CO2 out of the water, if you add CO2 to the water, you make it more acidic. If you take CO2 out of the water, you make it more basic because you're driving it this way, right? Are we good? Yeah. Right.
It's like a relative concentration in the system based on.
But if those plants just can't leave the building, right?
No, they can't use that, but they can use this CO2. And if they use this CO2, the whole equilibrium is being driven this way, right? So these are equilibrium. Like if you had water and you had CO2 above that water, a certain concentration of CO2 in the atmosphere above that water, and there was no life present, you'd reach some sort of equilibrium, and the water, this is why rainwater is naturally acidic, because there's CO2 in the atmosphere, and that CO2 is dissolving into the atmospheric water and driving the pH down a little bit because it's doing this. And then if you add a lot of other H plus, it gets more. But if you add a lot of CO2, you're going to make your rain more acidic, you're going to make the ocean more acidic, you're going to make everything more acidic. But if you have a lot of photosynthesis going on, you're pulling this reaction this way, and it makes sense. We're taking ancient carbon that was stored in the earth, we're putting it into the atmosphere. That's making things more acidic. If we have a lot of photosynthesis going on, we're pulling CO2 out of the atmosphere. We're putting it back into stored CO2. You good with this? All right. So now go back to the question, and Darby, you want to take another shot at this? What do you think now that we've talked about this? Or you don't have to, you can pass. Okay. Over the course of a day. And why does it become more basic? Yeah, makes sense. So originally, the HTOTMs of the world did lots of research with pH probes because they existed before there were where you can directly chemically measure pH. They did a lot of their initial measurements of primary productivity in aquatic ecosystems by measuring changes in pH over the course of the day. The problem with that is it gets really complicated in terms of chemistry because how much the pH changes depends on how much underlying carbonate rock there is in there, because it's also messing with the pH. If you have a limestone basin, the pH is not going to change as much as if you have a granite basin, because the limestone's interacting with it. So it just gets really complex. So as soon as there were good oxygen probes, people stopped using pH as a measure of primary productivity, because it just requires a lot more chemistry to figure out what the heck's going on. So people like me, I spent, most of my dissertation measuring changes in oxygen in the water column so I could measure primary productivity. So a lot of my research focused on factors affecting primary productivity in Chesapeake Bay ecosystems. And, I used oxygen and I measured the rate of change in oxygen over the course of the day. So oxygen probes were my friend and my enemy, because that was my mechanism for measuring primary productivity. So if oxygen's being taken up, I know that we've got respiration going on. If it's being released into the water, I know that we've got, and it's what I love about it is, like, from a whole ecosystems perspective, it's this beautiful measure that integrates everything going on, all the primary producers, the consumers, everything going on in that water column. You just dip an oxygen probe in there twice a day, in the morning and at night, and it's telling you, what did everyone do in there all day? What were they all up to? How much were they fixing? What's net ecosystem productivity in that system? So it's, from my perspective, an incredibly elegant way to measure whole ecosystem metabolism, which is very cool. Yes, Evan?
I think I'm still struggling on the concept, just because my original thought was plants photosynthesize taking up CO2. So if during the day more photosynthesis will occur, reducing the amount of CO2 present in the water, making it more basic.
Yeah.
Yeah.
So then at nighttime it'd be more acidic.
So you hit a transition point in the day, and the light is still out, but you're going to hit a transition point where photosynthesis exactly balances respiration. And then it's going to get a little bit darker, and then respiration exceeds photosynthesis. And then it's going to get totally dark. There's only respiration going on. And then the oxygen will drop all night long until the sun rises. And then you'll hit, it's actually a term for it, has to do with both time and depth, called the compensation point, at which photosynthesis exactly equals respiration and there's no net change. And that's when you get this sort of balance of that. Yes.
Just it's like opposite though from terrestrial. That if we consider like the water to be kind of equivalent to the soil in terms of that's like the substrate that the primary productivity is happening in, the soil gets more acidic with more primary productivity, right? Whereas here we're saying water column is more basic with primary productivity.
I think your thinking is really good here, but I think I think the time scales we're talking about are just so different. The problem with a forest is that it's really difficult to measure primary productivity on a daily basis. It's just like, it's very complicated to do. Whereas in an aquatic body of water, when I'm talking about this, I'm talking about changes that are occurring over a 24-hour period. And it's very difficult. You're thinking, when you think about like what's going on in a forest, when I hear you talking on a much longer time scale about organic matter being deposited in the forest floor, decomposing, and processes being different. It's just, you can't easily measure primary productivity on the same time scale in a forest. I mean, you increasingly, I think you can use radar and use LiDAR and stuff and make inferences about what's going on, but it's not as clean a measure as you've got, and it's a different time scale. So I think your thinking is good here, but I think it's just a different time scale we're talking about here. So I don't think it's comparable. What the two things you're talking about, I don't think are comparable, because it's really different time scales and long-term versus short-term processes. Does that make sense what I'm saying?
Yeah.
All right, so I do want to get to the case, but I want to say a couple big things, and I'll go back to terrestrial stuff before doing that. So one thing we did not quite make it to is when we were talking about ecosystem forming factors was sort of long-term time dynamics. And I kind of want to talk a little bit about these because they do relate so closely. They link energy and materials. And so there's this very famous paper that Eugene Odom, so one of the Odoms, published in 1969, which has, I think, a title that encapsulates the problem of anthropomorphism in ecosystems, the strategy of ecosystem development. And strategy, I would say at this point, doesn't feel like quite the right term because it implies that ecosystems have some sort of strategy, and I don't think they actually do have a strategy. But nevertheless, what he was trying to do is generalize about what happens as ecosystems mature with respect to energy capture and respect to how they process nutrients. And what he pointed out that is true in ecosystems. By the way, I'll make a statement about my career that might be relevant to your own career. So I got a degree in forestry, and then I got a degree in plankton ecology. And there was some sort of strategy, because I'm a human being and human beings can have strategy. There was some sort of a strategy in that, because the problem with forest from the perspective of graduate education is they are very slow moving systems. It takes a long time for a forest to develop. So if you want to measure, if you want to be involved in measuring ecosystem development in graduate school, the best you can do is have a little piece of some much longer term process of measuring ecosystem development, because the forest is going to take hundreds of years to develop, and you do not want to spend hundreds of years on your PhD. It's just a bad idea to plan that way. Plankton do what forests do in the course of days. So you can go through a complete course of planktonic evolution in like a 30-day period, as opposed to hundreds of years. So the shift from forest to plankton actually made a lot of sense for someone interested in ecosystem development, because they're obviously different ecosystems, but they do exhibit the same sort of patterns. It's just those patterns are so condensed in time in planktonic ecosystems that you can do a lot of experiments on ecosystem development in a planktonic ecosystem that would take hundreds and hundreds of years to do in a forest ecosystem. So I'm just saying, when you think about your graduate education, thinking about how fast the organisms or ecosystems you're studying move and can respond to manipulations that you might subject them to is worth thinking about in terms of like how long it's going to take and what you can do. So these are general patterns observed in different kinds of ecosystems. Partly what I'm saying is like these patterns occur super fast in planktonic ecosystems and much slower relative to the human lifespan in forest ecosystems. So as they mature, they tend to trap more photosynthesis. So that forest is capturing a lot more energy. A lot more of the solar energy landing on the forest is turning into biomass than energy landing on the agriculture or the other ecosystem, because they've got a lot more leaf area that's trapping that stuff. So that's a thing. The ratio of photosynthesis tends to shift. Early on, after a farm field is abandoned, you're going to have more decomposition, or after a forest is burned down or chopped down, you're going to have more decomposition than you're going to have photosynthesis. And then you're going to go through a period when you have a lot more photosynthesis than decomposition. And then that's going to slow down as the system reaches what we call in a form system steady state mosaic, when you're coming closer to a balance. So that forest on the North Field, that's primo for capturing carbon right now. That's about the best state right now, because it's capturing way more energy than it's being released. So it's in this sort of intermediate stage around here where it's much, much greater than 1, your ratio of photosynthesis to respiration. Biomass tends to increase as the ecosystem matures. How much the system holds on to nutrients also tends to increase. A more mature ecosystem, so this is stated as nutrient loss. I'm thinking of it as nutrient capture. A mature ecosystem hangs on to its nutrients. A young ecosystem does not hang on to its nutrients very well. Now, biotic regulators are a little bit more complicated, but that's how much the ecosystem is controlled by the plants that are there. This is a term that Stuart Chapin, who is part of our readings, talks quite a bit about. biotic regulation, the degree to which that the biology is controlling energy flow through the ecosystem tends to increase over time. So that forest, you walked in there, and one of the things we noticed, a lot less variability in temperature. That's because the forest is controlling its environment a whole lot more than the field is controlling the physical environment. So it's exhibiting more control. Positive feedback tends to be more important early in ecosystem development. Our selected species are all about positive feedback, rapid growth. Negative feedback tends to be more important later in ecosystem development. So this is, and this would be more like forest type ecosystem, although this is, I don't know quite what this is, because forests would actually have a longer time scale. But this is showing you early on, you've got more respiration than primary productivity. So this is, let's see, yeah, this is probably net primary productivity. And then you've got an exceeding respiration, so you're accumulating biomass. And again, our forest is probably someplace around here where you have this maximum excess between primary productivity and respiration. And as it matures and moves towards a steady state mosaic, it's still going to have probably photosynthesis in excess of respiration, but it won't be accumulating carbon as rapidly as it is now. Does that make sense? Important to understand these sort of patterns of change over time. And why did I put these little guys on here? So your biomass is going to be the biomass you're accumulating. So this is a stock, these two are flows. Your biomass is initially going to go down early in ecosystem development because respiration exceeds photosynthesis. And then once you hit this balance point, biomass stored organic matter in the system is going to go up. And it's going to be going up most rapidly at this point right here. That's going to be the steepest curve. And again, that forest is primo for sequestering carbon right now. And then as it gets older and you move towards that mosaic steady state, it's going to be shifting to that. Is this making sense? Okay. And again, nutrient loss. So I'm just sort of graphing in these things over time. I just want to land on one more slide, which is particularly relevant to our forest before we talk. And this is in one of your readings as well, because this is sort of the classic study of forest accumulation. This is by two gentlemen, Herb Borman and Gene Likens. And I was fortunate to take Herb Borman's, I think his, I don't know, maybe second to last class that he taught at Yale School of Forestry, but both of these guys are very, very famous ecologists. And they came up with a model of forest growth and discussed 4 phases. They were interested in forestry in particular. And they did the neatest experiment at a forest called the Hubbard Brook Experimental Forest in New Hampshire, where, I mean, kind of brutal from an ecological standpoint. They studied whole watersheds. Basically, in the White Mountains, there are a lot of little mountains. And so there are a lot of isolated little watersheds right next to each other, where all of the water falling between these mountain valleys all falls into separate streams. And so what they could do was really, from a whole ecosystem measurement standpoint, what they could do is incredibly cool. They built little dams on each of these rivers, draining each of these basins. And they built dams, this is called a weir, a V-notch weir. And they could measure how much water was coming out of the system, and they could measure the chemistry of the water coming out of the system. So it had this great controlled set of whole ecosystems, and they cut all the trees down in one, sort of simulating a severe storm event in New England that would have knocked all the trees down. And then they sprayed herbicide all over it with helicopters. Might seem like a bad thing to do, but it's a really cool experiment. Just keep the stuff dead for a while. And then they trace differences in sort of water flow out. Anyways, this beautiful, beautiful experiment that they use to develop, to create data to develop this model of patterns of forest development. So you have this severe disturbance. In their case, it was logging, but they left everything in place. And so you lost a lot. This is the amount of total biomass in the system. You lost lots of biomass, and then you and right after you cut it, you have a lot of decomposition. So that's what this line is, a lot of loss of biomass. And then you begin to get regrowth, and you've got this this phase called aggregation, where you're building a lot of biomass, transition where you may actually lose some biomass, self-thinning stage, and then a mosaic steady state occurring after that. So we're someplace in that forest in the north area, we're probably someplace around here in terms of the aggregation phase of ecosystem development. But again, this is all about primary productivity, storage of that. So we've got reorganization, increases in plant biomass, decreases in total ecosystem biomass. So plants are growing, but the soil is respiring. And then you've got this, building up of biomass as the trees grow, and then you've got the transition, and then you've got the mosaic steady state at the end. So I'll paint that picture in big force. And now what I want to do is transition to our case study. So this is a case study looking at two different ecosystems. So the two different ecosystems are the wetland ecosystem. Exactly, did I give you for this? I just want to see what I gave you. You've got the wet. You've got the wetland ecosystem outside, and then you have the living machine ecosystem. And I'd ask you to write out some hypotheses. And what I want you to do is get together with maybe the three nearest neighbors that you have. And here we'll do 1, 2, 3. So Darby's part of your group, you three. We're missing someone. Are we missing someone here? Yeah. So you three, and maybe you 4, if that's okay, if that works okay. Or you can do it 2 or 4. What do you guys want to do?
4.
Okay, you'll do 4. Okay. And what I ultimately want you to do is what you have here is light data. And I want you to sketch in what you think the oxygen data looks like in the pond for this. So that's your first job. So I want you to get, based on the discussion we just had, what should that look like? And then when you're ready, I'm going to give us data on that. So your job is to talk about what you expect and why you expect it, and then sketch it out. So that you apply everything we just talked about.
But like,
I agree. For the process of, I think
yeah.
So give your example, yeah.
So we talking about the opposite. Yeah. I was thinking that the model would increase during mid hours, decrease during night hours. As opposed to. It's basically acting time. Was what? No, I was thinking it was because
And share my screen again. So just go to this, go to here and then click on energy flow, and then it's linked right here. Just click on data. Oh, you can't see my screen? Why can't you see my screen?
it's too.
Oh, how irritating.
It's case name.
It says case data. Yes, it's data, case data. Yes. Let's see the display.
Oh, case, yes, is it the first link or the second link?
It's the second link. It's the one that's next to metabolism.
Oh. I found
It's next to the one that says metabolism, because that's what we're working on. Let me get this thing, extend displays, data displays. That's right. All right. Bear with me for a second here. Just make a copy of it, just save as and save it with a different name, and it'll save for you. I want to do that so that we can work on it together, but we're not working on it directly together, so that you guys got your own copy you can play with here. All right, so let me get mine up here. Sorry, bear with me, I'm having screen issues here. All right, so everyone should be looking at a spreadsheet that looks like this. You guys with me? Just get mine full screen and make it a little bigger so that those of us who are more challenged by seeing can see what the heck I'm doing. All right, can you guys all see that okay? So this is data that was collected with dissolved oxygen probes that were deployed into the pond, right? You guys with me? So this was every hour, it was collecting a new set of data, and it was collecting data on two things. It was collecting data, well, three things: dissolved oxygen, pond temperature, and photosynthetically active radiation. So what you've seen so far is the photosynthetically active radiation part, the PAR. And remember, we talked about the different kinds of light. PAR is what the plants see. So I used a PAR sensor so that I'd have a measure of what the aquatic plants in this case are actually seeing. You can see the data is actually quite old. I did this many years ago, but it would be no different today in general form. Now, so we're going to do a little bit of work with spreadsheets here. The first thing we want to do is get this thing. Let's see if we can do this. I want to freeze this column. Let's see, view, freeze up to row 12. So click on row 12 and then under view, freeze up to 12. Well, I just saved it as XLS. I said yes. So you guys made a copy of this, right? So you're working on your own version of this, so you want to save as and just put any name on it. The reason I did that is so I can scroll down to the bottom here and look at it separately at the time. See how I can do that? That's why I wanted to freeze it. Yeah. So that's just a trick that you can do. And now what we want to do is, now listen to me carefully, because this is a little funky what we're going to do here. We're going to click on date and time, and then I'm going to press shift, and I'm going to click at the bottom here so that I get that selected. And I'm going to click on Pondio. I'm going to click my control button now and click on Pondio, and then click on the bottom here. Oops, I didn't do that right. Hold on, let me try this again. I'm going to do a shift click down here, and then I'm going to do a control click up here and a shift click down here. Oh, Darn it. Excel is a little different. Never mind. What we're going to do is click on date and time, and we're going to click all the way down here on PAR. Yeah, we're going to click all the data. It's going to be a little bit buggered because the deal is PAR is on a really different scale, which is going to be problematic, but I think I know how to deal with that in here. And then we're going to click on data, and I want to graph this damn thing. Right, it's an insert. Yeah, sorry. My brain is like currently in Excel right now. No, well, we can't because we're now doing it in this, and we want to go to yeah, Excel would have done what I just tried to do, and chart. Yes. Now, hopefully I'm going to be able to figure this out. That's good. And I think what I need to do now, so I'm seeing what I saw. The problem is I can't really, so it is doing what I wanted it to do, which is graphing over time. But my problem is I need a different scale for temperature. And I want to add a secondary scale to this. Does anyone have that fresh in their head for, what's that? What's that?
Yeah.
Yeah, because what I want to do is add a secondary axis for, no one knows how to do this. You don't want to switch rows and columns. Well, let's do this for a second. We can click on PAR. How'd you do it? So you have your graph selected. And then we go to series, okay? PON-DO. All right. Well, that's buggered up though, because it's giving us bar graphs.
Or just understand, yeah.
Yeah, there we go. Okay, this is good. This is good. So key question here. Was everyone able to do that? I went to setup and line chart. Yeah, help each other if you're not there. Are you guys not there? Or are you guys there? Let me go back a little bit and try this over again. Okay, everyone who did not do this, bear with me for a second and let's try to do this together. So you guys got this.
Yes.
You got this. Okay, so what we're going to do is go to customize, and we're going to click on the one that is PON-DO. And hold on, help me out here. Series. Instead of apply to all, we're doing apply to PON-DO. Yes, right. Change left axis to right axis. So now it has two separate axes. And then we've got the problem of it did bar graphs. And then we need to go to chart style. And no, it's not chart style. We go to setup. We go to, instead of combo, we go to line. Is everyone with me now? Yeah. Sometimes we've done Excel. We'll see about Google. Everyone has it. Not everyone has Excel, so that's the thing. All right. So what we're seeing here, and this is, by the way, guys who are doing the guys who are in the group that's going to look at the pond over here. This is how we can measure productivity. Now, is anything surprising about what you saw here? My guess is that it's not quite what you thought it was going to be. Is it? How close were you guys in your estimates? Yes, I've used them.
First said it was gonna go down to 0 on DO on it. So, but we did have like the offset.
Yeah, it does not go down to zero. It would be a very different ecosystem if it went down to zero, because it'd be going anaerobic every night. It would be really, that'd be a very, like, things would die, all the fish would die. If it went down to zero, they'd all die. So yeah, you don't want it to go down to zero. You don't want it to go, like, for living things, if it goes below, 6, your fish are gonna be hurting something fierce. So it doesn't do that. Anyone else? Yes.
I mean. Think about it, but they won't go to 0, it's 1.
In terms of,
Geo.
right. Good. So I could regraph this from 12 if I just wanted to expand this so I could see it broader. That's a perfectly fine thing to do. But I was thinking you guys would say you were expecting it to be curving, the lines to be more curving. Did you guys have more curving? Yeah. It turns out that it does curve, and we can graph primary productivity, and we can do that in a second here. But notice that it does go up, and then it reaches a point here. And notice its transition point is not at exactly 0 light. It's someplace around here. This is sort of the compensation point when it starts to flip. When light basically, when this flattens out, that means photosynthesis equals respiration. And when this starts to go down, it means basically respiration exceeds photosynthesis. And we use this part of the curve, the rate of decrease here, the slope of this line, as a measure of respiration in the ecosystem. And this increase, so here, key question for you guys, is this increase, what is that? What variable is that? If I was to measure the rate of increase here, so the change in DO over the change in time, what am I measuring when I measure it during the day? What is that a measure of? Which of the factors? What? No, which of the terms that we discussed is it? It's a rate. Well, what is it a measure of? I just said this is your measure of respiration. This is a measure of what? Yeah, but which one? I mean, I just gave you a bunch of definitions of different kinds of primary productivity. What is that a measure of? Yes. Net. And why are you saying net primary productivity? Right, okay, but why is it, tell me, why is this net primary productivity and not gross primary productivity? What's going on all day in that pond? Respiration. So this is the excess of O2 produced over what's being consumed the whole time, right? So if I wanted to estimate gross primary productivity in this system during the day, how would I do it? How would I estimate gross primary productivity during the day? Yes.
Oh.
You had your hand up.
I know, I don't know why I did that, but I'll try.
I just want to say that that's like having taught like 5th grade, that's like totally 3rd grade, where you ask a question and everyone has their hand up and you call on them and they're like, yeah, I don't actually have an answer, but I really wanted you to call on. I'm just teasing you, Darby, but it's like, it was bringing that back to me. It was bringing it back. It's like, you call them, they're like, and what's the answer? They're like, oh, I have no idea what the answer is, but I really wanted you to call on. Yeah, there was. Right after I graduated from Orville. It's fun. 5th graders are awesome. They're as cool as college students. They're like, okay, so I'll give you a little tidbit on 5th graders. You reach this pinnacle of intellectual development in the 5th grade, and then adolescence, puberty hits, and it just totally takes you down. And I feel like you don't actually fully recover and achieve the intellectual potential of a 5th grader until you're in your mid to late 20s. I mean, that's honestly the way I think the trajectory works, because you get too preoccupied with like sex, reproduction, and it just completely distracts you. Like the fifth graders, they don't have any of that. They're just like strictly interested in like how things work, you know, and then the complications hit in. And of course, it's worse in like, you get to like 7th, 8th, and 9th grade, and they're just, I don't know why we bother teaching them anything, to be perfectly honest. They should just be out running around doing their thing. And then you guys are in the full recovery phase. So if you're thinking about like the model of forestry organization, you're like well in the aggregation phase. You haven't hit the steady state mosaic yet, but you're in the aggregation phase, if you want to use that as a metaphor for intellectual development. But the fifth graders are at this sort of pinnacle. I just want to say that. They're really awesome. Fifth graders, it's the best age. What? Puberty is a severe disturbance on the system. I think frankly, a lot of us spend the rest of our lives recovering in one way or another. But anyway, gross primary production. So how would I measure net? How would I measure? I mean, this is net primary production. I throw myself off. How would I measure? Gross primary production? And it's only an estimate. I can only estimate it. There's no other way to do this. Yes.
I think. Can you figure out sort of what your respiration rate is based on how much sun overnight?
Yes, I use my nighttime respiration, and this is an assumption, which is not actually a completely good assumption, but it's the best assumption we can make. We have a measure of respiration. This is what the ecosystem consumes in the absence of oxygen. And so I can simply add this respiration rate to this to get an estimate of how much they're probably producing. And again, it has the assumption that they're respiring the same amount during the day as they are at night, which is not 100% right. You know, maybe with the sun, they're respiring a little bit more, I would think, maybe because they're so actively doing stuff. But, you know, it's the best assumption we have. So I would simply add my nighttime respiration to this one to get a measure of gross primary production. Does that make sense?
That's something similar to sleep. I just realized I never thought of it.
They do, their photosystems do recover, you know, during the evening, you know, and I think it probably depends a lot on the particular plants. But I just want to point out, we're running down on time here, but I want to point out that we can calculate net primary productivity or gross primary productivity. So I'll write GPP here. We can calculate that at any hour of the day when there is light. So let's try this in cell 21 by just saying this equals my DO at this particular time minus my DO at this particular time. So my change in dissolved oxygen divided by, and this is going to be a little bit complicated, my time here, so this time minus this time. Now, the reason I said it's going to be a little bit complicated is because I need to actually, because Excel and Google Sheets think in days. So if I want this to be expressed per hour, I need to multiply this times 24. Because it's when you subtract one time from another in Excel or Google Sheets, it's expressed in days. And so I need to multiply it by 24 hours. And I could just say that's it, but I'm just saying like my definition is per hour. So you're right. It's just one. So it's not going to be different if I don't divide it by that. But I want to be explicit in saying my rate of primary productivity is my delta oxygen divided by my delta time. So this is the definition of rate. Now I could copy that down. And of course at nighttime, it's no longer a measure of photosynthesis. It's a measure of respiration. So what I might want to do is when there's zero light, move that over a column and call it respiration. And my units of respiration are what? My units of photosynthesis and respiration are what? What are my units here? And these are typical units that we would use for primary productivity if we were measuring, in water using oxygen. Yeah, these are the units I'm working with here. So it's not that, it's this.
I mean, so use Pondio.
It's a change in Pondio. My Pondio is in milligrams oxygen per liter. And we just expressed our time in hours. So my measure of primary productivity in these systems is milligrams per liter per hour. The nice thing about that is you don't need an aerial measure in these aquatic ecosystems because it doesn't matter how big the system is, milligrams per liter per hour. It's a volumetric measurement. So it's scale independent in terms of area. So it doesn't need to be per meter. You don't need an aerial basis for that. But I'll leave you with that thought. And yeah. I want to talk about living machine stuff too, but we ran out of time and we'll get back to living machine later and what's going on in those. Would I expect there to be significant photosynthesis in the living machine? Let me ask that question in the water column in the living machine. Well, maybe one question before that. What is the living machine designed to do with organic matter? Get rid of it. So what are we optimizing that system for? Primary productivity or respiration? Respiration, right? So that system we would expect to be basically be dropping its dissolved oxygen all the time, right? And so the way those tanks work is we bubble the tanks. Almost all the tanks are bubbled with oxygen because we're trying to deliver oxygen to them. And the way we have those systems set up is, and in fact, it hasn't been working for a number of years now, but the way they were set up for the first couple of decades is the different tanks had oxygen probes sitting in them. And those oxygen probes for much of the day would just give a pretty constant reading, and it would have to do with we were pumping oxygen into the tank and try to keep it oxygenated. And it would just measure, some concentration. It wasn't going to give you any measure of metabolism because you were delivering oxygen all the time. So you couldn't measure a change in oxygen. And so when I first got here, I designed the system in there to shut off the delivery of oxygen to the tanks every 6 hours. So every 6 hours, it would stop delivering any oxygen to the tank. And at that point, what would you expect to happen to the concentration of oxygen in those tanks? If you stop delivering oxygen to them, what would you expect to happen if they are in fact dominated by respiration? It would go down, right? So as soon as you stop delivering oxygen, you'd expect them to the oxygen to just start dropping. Now, here's the key question. If you were to look, so it's a series of tanks in the system, presumably you're chewing up organic matter as you move through the system. Where would you expect in which tanks would you expect the drop off to be largest? And in which tanks would you expect the drop off to be smallest, going from input to output? Where would you get the most dramatic decrease in oxygen per time? And where would you get the slowest decrease in oxygen per time?
What's the difference between?
Well, water flows through a set of tanks. So imagine that it goes linearly through this thing, through a series of tanks. The first tanks, and we have names for these tanks, the first tanks that are aerated are called CA1 and 2. And the last tanks in the system that are aerated are called OA3. So between CA1, which is the most upstream tank, was closest to raw sewage, CA1, and OA3, which it's been bubbled in a set of tanks all the way there. What would I expect the graphs to look like for dissolved oxygen after I shut off the oxygen to the tanks?
There'd be a huge decrease in the first tank and gradually less and less as we get farther away from the sewage.
Right. So the slope of my drop off. So we were looking at that graph on this. So imagine we're kind of in this portion right here. So I've got a tank what you're saying is in the first tanks, I'd expect a really steep drop because there's lots of organic matter, lots of respiration. And then as I move through tanks, it would crank up like that. Does that make sense? Let's actually have that graphed here. I don't think I do. LMTO. Let's do a quick graph of this one. So this is the second worksheet here. I'll just stop there and graph that. You guys can do this at the same time. All right, so this is actually a continuous measurement of oxygen in this particular tank here. And maybe I should spread out the scale here a little bit. Let's see, where does it let me do scale? Min, right, so min, let's do it from 6 to, that's good. Okay, so let's look at these tanks. Okay, so what you're looking at, explain to me what I'm looking at here and why I see what I see here. What is clear about how the system is set up?
So 4 is shit.
Yeah, so pretty clearly, this is when the thing was set to shut off oxygen to the tank. So you're seeing them just sort of, you know, it's some sort of semi-stable thing. There was another shut off back here, which is why you're seeing them ramp up a little bit, because there's another shut off back here. So they're still climbing a little bit after that last shut off before this particular one. But what do you notice about, so I could calculate the rates here by the delta oxygen, the drop from what looks like, 8.6 down to 8.3 or something over this. I think I had them shut down for like that's 5, I think it was a 45-minute period I had them shut down for before I started oxygen up again. So that drop over 45 minutes, the delta oxygen over delta time, 0.75 hours. So it would be, it said it would be 0.5 DO over 0.5 hours, about 1 milligram per liter drop is a measure of, it's like about 0.1 milligram per liter per hour rate of respiration. Does that make sense? That's what that line is. It's something like that. I'm not looking at numbers here, but that's a guesstimate of what that is. So this one is my OA3 tank. So this one is the one that is farthest downstream. This is my CA tank. Right, so this is my closer to input. This is the first tank that's bubbled. And what do you notice about the steepness of this one versus this one? Yeah, it's much steeper, so it makes sense. There's a lot more organic matter to be respired upstream in this system than downstream, because the system is basically chewing up organic matter as it moves downstream. And we could easily calculate the rates of these things simply, again, it's just the change in oxygen over the change in time is by definition a rate. It's a change in something over the change in time. So these are measures of respiration in the tank. And so what that tells you is the living machine is kind of doing its job in terms of taking organic matter and turning it into CO2 that goes up into the atmosphere and leaves the tank, and is getting rid of that organic matter from the water. All right, I think we are now officially done. So same processes, primary productivity, respiration. You can measure them in aquatic systems. You can measure them in terrestrial ecosystems. And the way in which we do this is different. The time scales at which we can do it are different. And if you want to do a PhD, aquatic ecology is the way to go.
Thank you.
I still love forests, though. I will tell you, the other reason I went into marine science is because I thought it would keep me on the coast, and I really wanted to be on the coast. That's where I wanted, and look where I am. I'm with you guys. Yeah, and I don't count that. Ocean. I have a pond. I have my little bit of aquatic ecosystem in my backyard, which is nice. We have good crayfish around here. So we got the crustacea. What? There are lots of crayfish around here on the land. Yes. You can see little chimneys around here in various places. Yeah. What? I don't think there's like a crayfish industry here of any kind. I've seen crayfish that look like they're edible size in Plum Creek, but not big ones. We're not talking like Louisiana style crayfish.
No, it's just like.
Oh. Thank you, Professor.
Yeah, take care. Take care, Jackie.